Okay, for this module, we're going to work on vertical motions. Air moves in 3 dimensions, as we've been talking about for the first 4 weeks. Everything in the atmosphere is 3-dimensional. So the vertical motions of the air can have a major impact on things. So, for example, on average, the entire atmosphere, if you averaged it out, would be not moving at all, upwards or downwards. So if you start with a rain cloud, for example, fairly weak, just giving light rain, you get about 10 feet per minute vertical motion. Or a weak thermal, like out in the desert, if you see gliders and work on them and all that, and probably down in the Caribbean some, you get about, 200 feet per minute. Yeah, moving a little bit. A growing cumulus cloud. Ever fly through one when you're coming in for a landing down there at Vero Beach? Bounce around a little bit, about 500. And then you get into thunderstorms, and you get into strong thunderstorms, about 5,000 plus feet per minute. Mountain waves, extreme ones, can go up 5,000 feet and down 5,000 feet per minute. Just like clear air turbulence can. So that gives you a concept of the scale we're talking about in vertical motions. So what causes these vertical motions? Well, one of the main causes is convergence. Convergence is just winds coming together. So if you see the wind, a sea breeze coming inland in Florida, coming in off the water towards the land. The land, on the other hand, may not be moving that air at all or whatever, so it's just sitting there. Well, that air needs somewhere to go when it comes inland, so it goes upwards when there's convergence. Now, by the same token, if the air was blowing off the coast of Florida and the air over the land was not moving at all for any reason, then there would be divergence. The air's got to come down from above to fill in where the air moved away from it. So you can get divergence and convergence, and you get them at different levels. So that's one of the interesting things in the atmosphere. When you watch lows form, and we're going to talk more about that here in another week or so, lows form when there is divergence aloft. Think about it. The air is spreading apart aloft, so where is that air going to come from to fill in? It comes from down below. Well, the air down below causes rising motion. So if you can get convergence at the surface where that air started to go up, and the air really is going up, you're getting lower pressure down there, so the air is converging more. So that's how a low pressure system begins, with divergence aloft, convergence at the surface. High pressure is just the opposite. You get convergence aloft, pushing the air down, building the high below it. So they work together in tandem. Mountains impact vertical motion. If you fly along and coming towards a mountain range in West Virginia, you're going to hit some winds up or down, depending on which way the wind is flowing. If the wind's coming out of the northwest in West Virginia, as you're coming into the mountain, you're going to feel a lift in your plane as the air is going to be trying to go upwards. And when you come on the other side of the mountains, come out into Virginia, plane's going to want to go downward because it's going to have a sinking motion. And there are mountain waves that form because of these, and they're partly due to stability and all, but the strongest mountain waves are always going to be the closer ones to the mountain. So in other words, as you're coming in towards the mountain, the intensity of the vertical motions are going to increase. So keep that in mind. If you're having trouble on a flight coming in towards a mountain, try going parallel to it for a while. Maybe you'll find a pocket of air you can go better. Otherwise, maybe try, even if you have to, go back around it. And you'll notice that these go up pretty far in the atmosphere. I had a professor once that told me a mountain impacts the air for about 40 times its height. So that's a long way up. Fronts. Warm air rises up over cold air. We talked about densities last week. We know warm air is less dense than cold air, so it's going to have a tendency to rise. So if it rises over warm air or cold air pushes out the warm air below it, there's going to be some vertical motion that occurs from the orographics of that. Another one would be convection. Think about hot air rising basically with convection, or sinking if it's cold air. And we're going to deal with stability here in a minute. And that's really where this convection plays a big role. There's also mechanical turbulence. When you're flying low, you'll see clouds maybe in streets out ahead of you. There'll be a cloud deck, nothing, another one, and so on. There may be just stratus clouds fairly low, maybe 3,000 to 4,000 feet, or even cumulus. When you fly through that area, if you're at that altitude, you're going to have a little bit of turbulence every time you fly through one of those clouds and as you're moving along there. And that's mechanical turbulence. The winds, the roughness of the surface of the earth causes the winds to roll with time. They form eddies. And what you're basically seeing in these clouds is eddies of air going up and down. Gravity waves are another means. And they're a little more complex, but they develop in a certain layer of the atmosphere, and they can really get strong sometimes, especially if conditions are exactly right, basically around low pressure systems usually. And if they do develop and you're flying through one, you're going to bounce a lot. They're going to be generally fairly low level, 6,000 to 10,000 feet mostly, sometimes a little bit higher, but they have a major impact. Sometimes they can produce tremendous winds at the surface, and they can even produce really heavy rain or snowfall. Stability. So, cooling air expands as it's going up, and that develops. If it's dry, that air is going to cool at 9.8 degrees Celsius for every 1,000 meters. So, if that air is dry, if you have an air parcel, and an air parcel can be any size. It can be 1 foot across. It can be miles across. If it's going up, say up the side of a mountain, that air is going to cool by 9.8 degrees for every 1,000 feet you go up. So, for every 1,000 meters you go up. So, in the Appalachians, for example, which can go up to about 4,000 or so, maybe 5,000 in some down in North Carolina in a few areas, the temperature, when it started up, will have dropped over 9.8 degrees by the time it hits the peak. Now, everything is off if you have moisture. That completely changes this. Why does it change that? Well, we've talked something a little bit about latent heat. But when the air parcel is rising, and if it reaches saturation, what happens? It releases heat into the air. So instead of cooling at 9.8 degrees, it's going to cool around 6 degrees for 1,000 meters. That 3 degrees Celsius makes a huge difference in what happens to the stability of that air parcel. So let's take a look a little bit at this today, what's going on. Here is a relatively current surface weather map. There's a warm front coming into West Virginia, across parts of Ohio into Indiana and Illinois, and a cold front back here. So with that, you would expect convergence right immediately along a cold front. Cold fronts are very steep, so they tend to push just out ahead of them the air up more. So you more tend to get a line of storms or more convection just out ahead of it. Warm fronts, on the other hand, are shallower, and many times the convection will form down to the south of it because the convergence is occurring maybe aloft. So let's take a look at that now with what's happening. This is real time. Notice how the thunderstorms and all are developing just to the south of that warm front. They're actually in the warm air at the surface, but they're in the cooler air aloft. Then on the other hand, this is probably right along just a little bit ahead of the cold front. So things are kind of working as you would expect. There's convergence down here, convergence up here, one with the cold front, one with the warm front. And this is something called moisture convergence. It combines the air converging and the amount of moisture in the air to see where the best moisture is converging. That tends to be where a lot of thunderstorms develop, and you can see it. It's just on the south side of the warm front, but just to the east of the cold front. So let's take a look quick at a sounding, and let's talk about stability again. Here's Nashville in the warm air now, but this morning it was not. Current air temperature is 86 at Nashville. That puts it over here somewhere. So instead of this little inversion of sound temperature, we're over here, about right in this area. So if it's going up dry adiabatically to right there, we'll say, something had to push it up, and that's the front, the convergence you're seeing. This air had to have something to cause it to lift. Once it lifted to that point, here's where it became saturated. And now it's following what you would call the moist adiabat, which is over here. Dry adiabat's going here. So this air parcel from here on out is always warmer than its surrounding until it gets up to here. In which case, it's, pretty far up in the atmosphere, maybe 40,000 feet or so. It's not very far over, but it's a little bit over. So it's going to be accelerating. You take a hot air balloon, you put some heat in it, that air balloon starts shooting upwards very quickly. The same happens with these air parcels. Once they're warmer, than the surroundings, they are going to accelerate upwards. So this, combined with the motion of convergence down here, is going to be pushing this air parcel upwards, and that's what's causing these thunderstorms we saw. So you can see how this all works here. If this would have been dry down in this layer, we wouldn't have had any moisture. We'd have been coming over here fairly stable. It would have taken a lot more energy, a lot more convergence at the surface to make this air parcel rise. Now we had enough convergence, we could push it up, and it didn't take a lot. So that's why the thunderstorms are going there. Finally, just looking at this on the satellite image, we can see the warm fronts up here. Here's these showers and thunderstorms developing down here, just south of the warm front. And just to the east of the cold front are the more showers and thunderstorms. So everything is working just like we were talking about in this section. So you can see the impacts of vertical motion. And if you look at it here, I want to make this loop move now, because I want you to see something with the eastern side today. Winds are coming from the east, northeast today, here. Which side of the mountains are the clouds on? They're on the east side. They're being forced up there, and they're sinking on the other side. So there's actually some clearing that's occurred in parts of West Virginia today because of that. So you can see, again, orography playing a role. So hope you got something out of this, and we'll go on to the next section here in a minute.